So in this video we want to develop the idea of a directional derivative. So here's the idea. If you calculate the partial derivative with respect to x, and then you evaluate it at some input x naught, y naught. So we calculate the partial derivative, and then we get the specific value of that derivative at x naught, y naught. If you're doing the partial derivative with respect to x, you're finding the slope of the tangent line at the point x naught, y naught, f of x naught, y naught, right? There's going to be a z naught that goes with it. You're finding the slope of the tangent line at that point, but in the direction of the x-axis. So you know the rate of change in the direction of the x-axis. And similarly, if you calculate the partial derivative with respect to y, and then you evaluate that partial derivative at the input x naught, y naught, then you're finding the slope of the tangent line to the graph at this point, x naught, y naught, z naught. But the slope of the tangent line that you're finding is the slope of the tangent line that's in the direction of the y-axis. And that's good, but you may not always want to know the rate of change in the direction of the x or the y-axis. You may want to know the rate of change in some other direction. So let's let u hat be a unit vector. So a vector of length 1 that's in the direction you wish to know the slope of the tangent line at a given point. So let's say u hat sits right here. So if u hat makes an angle of theta with the positive x-axis, which is how we usually measure angles, then u hat can also be described as the cosine of theta, the sine of theta. From trigonometry, we know that this gives us a unit vector in the direction, oriented in the direction of theta with respect to the positive x-axis. Okay? So the next thing that we want to do is think about, well, when we take a derivative, what are we doing? Well, we're finding the slope of a secant line. So let's say we know that we want the derivative in the direction of u hat. Let's draw u hat right here. So here's my u hat. We want to find the direction of the derivative in the direction of u hat at a specific point x naught, y naught, z naught. Well, what we want to do is establish a plane parallel to u hat, but perpendicular to the xy plane, so that that plane right here intersects the surface that we're working with, and it intersects it in a line right here. And so if we're finding the derivative in the direction of u hat, what we are looking for is the slope of the tangent line to the point in that plane. And then what we want to think about is, what is the slope of a tangent line? So remember in Calc 1 what we did is we found the slopes of secant lines, and then we took a limit that would allow the secant line to become a tangent line. And if we think about a secant line, then that would just be a matter of establishing another point, say x, y, and f of x, y, or z, another point on the curve that intersects the surface and the plane, and then finding the equation for the secant line, and then taking an appropriate limit. So remember, the secant line slope is just going to be its rise over its run. So if we've established some second point on the curve of intersection between the plane and the surface, if we've established a second point of intersection, we can drop perpendiculars from each of those points into the xy plane. And this point right here is going to have coordinates x naught, y naught, 0. And this point right here would have coordinates x, y, and 0. And then think about, how can you do an equation of a line? Well, we've learned just recently that one way to get the equation of a line is to take a vector from the origin to any place on that line, and then find a vector parallel to the line we're interested in. So u hat will be parallel to that line, and then just scale it. So we found equations of lines by taking, hey, here's a vector that gets me to the line, plus scale. So if the distance between these 2 points is t, the distance between these 2 points in the plane is t, we just scale u hat to get from this point to this point. And then u hat is just, we've represented it with u sub 1, u sub 2, or cosine theta, sine theta. So it turns out that we can parameterize any point xy right here on the line by saying, if I get to take the vector from here to here and then scale out to this point. So x is going to equal x naught plus t times u, and y is going to equal y naught plus t times u sub 1, and y naught will be t times u sub 2. So right here, what we want to recognize, if we're doing the slope of the secant line, it's going to be the rise over the run, but the run's just going to have length t. So the slope of the secant line is just going to be rise over run, and then we want to recognize that the rise is going to be the change in z. It's going to be the change in z, which is just going to be z minus z naught. But z naught is what you get when you evaluate the function that describes the surface at the point x naught, y naught. So z naught can be replaced with f of x naught, y naught. And then z is just the point you get when you evaluate the function at x and y at the second point. So this is just f of x and y. But we parameterized x and y. So we can replace x and y with their parameterization. So we can say, hey, this is f of x naught plus t times u sub 1. Got to get it to fit in there though. So it's going to be f evaluated at right here. We're going to plug x and y are equal to x naught plus t u sub 1. Y is equal to y naught plus t times u sub 2. And then we plug those parameterized values into the function. So it's x naught plus t times u sub 1, comma, plug y naught plus t times u sub 2 into the function. And this difference between the two function outputs is your delta z. And that's going to give you the slope of the tangent line, the secant line between those 2 points. And then what you need to do to get a slope of the tangent line, rather, is you need to let t, which is just the distance between these 2 points, you need to let that distance go to 0. In other words, we need to make this point Q approach the point P in the xy plane. So as we do that, as we let Q get closer and closer to P, this point here is going to move closer and closer to the point x naught, y naught, z naught. And if we take the limit, then as t goes to 0 right here, the secant line becomes the tangent line, and we have the derivative. And then we call this derivative the directional derivative in the direction of u hat. So the next slide concretizes that idea. So let f be a function of 2 variables. Let u hat equal u sub 1, u sub 2, or cosine theta, sine theta, if theta is the angle u hat makes with the positive x-axis. So let u hat be a unit vector, so it always has to be a vector of length 1. And if we do those things, then the derivative in the direction of u, the derivative in the direction of u hat of the function f at a specific point on the surface, x naught, y naught, z naught, is given by this difference quotient right here. And then what we're going to find is that there's a shortcut method for calculating this directional derivative. So just like in Calculus 1, we defined a derivative using a difference quotient, and then we calculated some derivatives using a difference quotient. But we didn't want to have to continuously use the difference quotient to calculate a derivative. So what did we do? We spent the time to come up with formulas for the derivatives of all kinds of different functions. So what we want is a formula for calculating the directional derivative without having to actually do the difference quotient. And it turns out that a directional derivative can be calculated this way. The directional derivative in the direction of u hat of the function f at a specific point x naught, y naught, z naught, you can find the directional derivative just by taking the partial derivative with respect to x and multiplying it by the x component of u hat, and then adding to that the directional derivative for y, the partial derivative in the direction of y times the y component of u hat. And then usually I'm going to be a little bit lazy and just write this as partial derivative with respect to x times u sub 1 plus partial derivative of y times u sub 2, with the understanding that we have to plug in the input values for the point for which we're interested have to be plugged into the partial derivatives for this to work out. The other thing to notice here, and this will become important in subsequent slides, is that this is actually just the dot product. If you put f sub x and f sub y, the partial derivatives with respect to x and y, in a vector form, and you dotted it with u hat, which is just u sub 1, u sub 2, this is exactly what you would get by taking that dot product, and we'll play off this a little bit later on. So here's the plan. The plan is, for the next two videos, I'm going to show two different justifications that establish that this formula right here gives you this directional derivative. So we're going to do the math. We're going to say, yeah, here's the formula for the directional derivative. Hopefully, conceptually, you're understanding what the directional derivative is. Hey, pick a direction vector and then find the slope of the tangent line to the graph at a point in the direction of that direction vector. This is something we want to do when we're not as interested in how are things changing in the x or the y directions, right? So that's the idea behind a directional derivative. Now we have a shortcut formula for it, but we're going to do the thing that math people should always do, and that's dissect the formula to understand why and how it works, so that we're not just taking for granted or taking on faith that a formula does what we are told that it does. So the next two videos, I'm going to do two different justifications. One will be an algebraic approach to justifying it. One will be more of a geometric approach to justifying it. And then in the fourth video, I'll actually show us using the formula to calculate directional derivatives. So the mechanical, kind of non-mathy part of it. Here's the formula, use the formula, monkey see, monkey do.